Hello everyone, myself Palak Chaturvedi. I am a software engineer at Microsoft.
Hi everyone, myself Nitin Jadhav. I'm a senior software engineer at Microsoft. Today, myself and Palak are going to talk about debugging data corruptions in PostgreSQL, a systematic approach. We will explain our experience on handling corruption problems first, and then we will summarize with the approaches to handling corruption cases, including best practices. The attendees can apply these techniques to avoid corruptions at first place and also learn how to detect and recover from the corruptions if it happens. Palak, can you switch to next slide? Hi everyone, I'm Nitin Jadhav. I work for Azure Database for PostgreSQL team. I have hands-on experience in onboarding major and minor versions of PostgreSQL as well as integrating new extensions into managed database environments. I have actively contributed to resolving customer incidents, including analysis and resolution of various data corruption issues. My association with PostgreSQL spans around 5 years, during which I have worked for PostgreSQL based products and also contributed to the community as needed.
Hello everyone, this is me. I am a software engineer at Microsoft, member of the Azure database for PostgreSQL team. I have experience in onboarding new extensions to FSPG, handling core downs and corruption issues, also making code changes to FSPG. I have been with Microsoft since June 2024. I interned in the same team. I have been contributing to PG community as well. So let's now start our talk. So this is the agenda for today that we have. We'll learn about what is data corruption, what are the causes that we have, and we'll have some analysis of few corruption cases. Also, Nikhil will tell us how about the general approaches to handle corruption cases. So let's start. So before debugging data corruption, first we should know what is data corruption. So let's start with that question. So data corruption is like amnesia for data. It's like the Postgres forgets whatever it remembered, like it had some previous data but it is something gibberish. It's like if you have a spreadsheet, you have very important data in it, but suddenly something goes wrong and instead of that numbers you have random characters that makes no sense to us. We can also say that these are unintended changes to the database. With respect to PostgreSQL, we can say these are the heap file table changes, index changes, or the wall file changes, or any important files that we have in our Postgres. Now let's learn about what are the causes of these corruptions. Like we can blame anyone for this corruption, but let's get to the real cause, which could be these three that we have figured out. First one is bad hardware. Like we can have a bad disk or bad memory or some faulty RAM that might flip our bits, or during the database is working and suddenly you lose the power, so that can also cause corruption. Second is bad software. Like there might be possible that there are bugs present in PostgreSQL, which is very rare, but maybe there are some bugs. Also, the bugs in kernel and OS. Also, the uh, antivirus tool that we are running or the backup tool that we have. All these can cause corruption. And the last problem that can be is you yourself. Like if you think a file is not needed and you delete it, like sometimes pg wall folders reaches to up to 100 GB, but and thinking that it is taking space in your system and you just delete it, it can cause corruptions. So now when we want to learn about debugging data corruption, first we should know, like where can this data corruption occur. So we'll start by learning about the logical layout of our database cluster. PostgreSQL runs on a single host. It has one database cluster. Database cluster is a collection of databases, as you can see, database 1, database 2, and up to n databases. And inside each database, we have tables, indexes, and other objects such as views, function, and sequence. So this is the logical layout. Uh, to identify each database, we have OIDs, and for each table also we have OIDs. You can look at them in the system catalogs that are present at a PG class and PG database. You just need to run a SQL query where it is shows select star from PG class or select star from PG databases, and you'll know what tables do you have and what the databases that are present in your system. Now let's look at the physical layout. Physical layout is more important because this is where actually the corruption occurs. So when you run a initdb command, that is, you run initdb a test. If you name our test is the name where we want to start our Postgres. So if you run that initdb command, you'll see some a data a data directory is started where the base directory is the test data that we have. Inside that we have multiple files and folders. Like in those files we have postgresql.conf file, that is the configuration file that we have for Postgres, where we can add like values for a few parameters. We have pghba that gives us about the connection that we can make, or the like the auth connections, and other folders such as pg wall folder and the pg like base folder and global. So let's look at the base folder. Base folder, when I do ls for base folder, we see multiple numbers like 1451642716498. These are the OIDs of the databases that we have present in our PostgreSQL that is running. So inside each of these folders, we have multiple tables, indexes, free space maps, and visibility maps. Each table has its own free space map and visibility map, except for the indexes. Indexes do not have visibility map. What do I mean by free space map is that when the free space map is a table that tells us the about the pages, how much free space is present in each page. You'll learn more in the next slide. Similarly, visibility map tells us if we can view, if a transaction can view a block for like, so the visibility map bits are set true or false for those. And now we have the global folder. Global folder is common to our entire cluster. It contains some control files, file load map, and internal files, also some system catalogs that we have. So the corruption can occur at any of these at any of these files that we have present in our base folder. But now we'll look how the internal layout of a heap type table file can look, because any part of this can also be corrupted, because these are just hex random bits, so anything can be corrupted. So what is a table file? When we create a table, we get a file in our data directory that has the OID of database and slash our table OID. So that consists of n number of blocks. Each block is of size 8 KB, and as as the data increases, our Postgres keeps on adding new blocks to it, and the size of the file increases. uh, the maximum size of the file that we can have is 1 GB. After 1 GB, like the new file is added with .1, .2, .3 extensions. So that is the maximum file size we can have. Now we'll look, as you can see from the figure, the page size is explained, like what is inside the page. So inside the page we have page header, that contains pd lsn, pd checksum, pd flags, pd lower upper, these kind of things. Like lsn tells us the last lsn that updated that file. Checksum contains the data about those, the checksum that we have calculated for that page. And there is lower that points to the end of the line pointer, and pd upper that points to the starting of the tuple. So line pointers are the pointers that point to each of the tuple that we have, and tuple are the actual table data that we have. And between these line pointers and tuples, we have free space that the free space map data contains. Like this is the free space that we have where more data can be added. Next, like now we have learned what where the corruption occurs. So like the this page header consists of 24 bits. Any of those 24 bits can be corrupted, or the line pointers can be corrupted, or we can insert random values in free space that can cause corruption. So now we'll have an analysis of the few corruption cases that we have. We'll cover two corruption cases in our study. So let's start with that. First, we have the could not read block error. So this error occurs like uh, this does not cause Postgres to go in a loop. It just is there, and whenever you try to look for that table, it throws the error that we cannot read the block and like read zero of some bytes. So that occurs. Now this occurs when PostgreSQL tries to read a specific block from table or index file but fails to do it. So that can happen during query execution or vacuuming. Like you are running a select statement and you have that corrupted file, then you will see that error. What are the causes? The causes are like the disk corruptions, like uh, the this might have corrupted some of the files, or the file system issues, or accidentally you have truncated or removed the file, or while backing up the partial file is backed up. So all that can cause the could not read block error. We'll look at the simple corruption that we have first, like that is the corrupted index. So what you can see the indexes that you have in your uh, database using the pgstat user indexes, and each index will give you a pg relation file path that looks like base slash 16498 16546. This the 16498 is the database oid and 16546 is the index oid. So like the pg bench branches primary key is stored in this relations file. So now we'll try to corrupt our one index. So what we use is we run a dd command that enters random data in our index that we have. So what we do is when we run a command like select count star from pg bench branches, it throws errors such as invalid page in block 0 of relation, the relation that we get. And when we once see what is the relation, we get something like the pg bench branches p key is corrupted. So that's easy. Like when the index is corrupted, you can just uh, use the command reindex and it would reindex the like create a new index, drop the previous one, create a new index, and everything would be corrected. So once we have that index is done, we can easily access pg bench branches and our corruption is over. Now we'll look take a look at a more deeper level of corruption that we have, which is very difficult to recover from. So what we can see all the tables using pgstat user tables, and we can similarly get the relation file path using the pg relation file path function that we have. So in my database we have these four uh, relations that we have, and I would like start corrupting one of these. We here I have used three methods. First one is dd, that is a low level code that corrupts a single file. Like right now I want to corrupt the 16498.16543 file. So it can be easily corrupted using the dd command. When I corrupt some bytes, like in this case I have corrupted a checksum. I like entered a wrong checksum instead of the earlier that we have. So when the checksum is not matched, it throws error like page verification failed, calculated checksum 9478, but expected something, and we get an error that we cannot read that page further. So like checksums are not usually on for all the databases. We need to turn that on for each database, like using set checksum equals to 1 something. And then once it's done, it runs a sanity check for our database, so that uh, the files are not corrupted, and we get to know when the file is corrupted or not. But the checksum is not turned on by default, is that because it's causes, like, since it runs checksum for all the blocks and pages, it is like heavy on a Postgres, and the memory usage is very high. So we sometimes we for large database it is usually avoided, but you can do that for small databases that you have. Second method is truncating a file, like you have a file and you remove some part of it. So when you do that, like you are reading a file and you run a truncate statement on your other command prompt, then it would throw some error like could not read block 1 of base something. And like, since the block you have already removed that block and made the file size of 8192 KB, so it cannot read that block one. So this that could cause the error. Third method is like, when Postgres starts reading our file, what it does is it gets the PG relation file size and then divides it's with the block size. So it then we get the number of blocks, and the MD read function reads for those number of blocks. What if the PG relation file size is corrupted, or like whenever when you were going to run it was different, and suddenly the file size has decreased, or the block is not present, or there are partial writes, then also we can see the error as could not read block. And that we have. Now I'll hand over to Nitin for the second case that we have.
Yeah, thanks, Palak, for the explanation. I'll continue from here. We have seen many cases of this type of corruption. So first, we need to understand when this can occur. So this occurs when the server is unable to read the checkpoint record during recovery upon start. So actually, what happens is if the server is not properly shut down, and then during the next start, it gets the checkpoint details from the PG control data file. So based on that, it tries to read the checkpoint record. So if it is unable to read it, either because of PG control data is corrupted or the wall data is corrupted, so then this issue can occur. Next is what can cause this to occur. We have seen some cases this issue was happened due to hardware issues, and some cases due to software bug. So I'll explain each of these in detail in the upcoming slides. So we have now understood when this issue can happen. Before understanding what can cause this issue, so we have to understand how to verify the data is corrupted or not. One indication is the log message. So here, the log message could not locate a valid checkpoint record. Is almost it indicates the corruption. But we need to verify a few other things before coming to a conclusion. For that, we can validate few data from the PG control data file. So we need to retrieve the content of PG control data file. From this file, we can get the latest checkpoints redo all file and the latest checkpoints redo location. And there's a tool called PG wall dump, which is used to read the content of the wall file. So this tool outputs the wall content in human readable format. So in the example mentioned here, the wall file name is ending with 54 and the wall location is ending with 28. I'll pass this information to the PG wall dump and try to read the content of this wall file. If the PG wall dump tool is able to read the data, so then there is no corruption. If it is unable to read the data, so then that indicates it's a data corruption. Next, let's understand what kind of hardware failures can cause this. So we have seen cases where the VM running PostgreSQL went down abruptly. So the reason for VM going down can be many, but such cases are common in managed database. And we have also seen some disk failures that cause this kind of error. Next, let's understand how a software issue can also cause this. So recently, we have seen some cases where multiple hard links were pointing to the same wall file. So this issue led to wall being overwritten and resulting in corruption. So the fix for this bug was initially implemented in version 16 and later versions, but it was not applied to the earlier versions. After many such reports, it is now backported to versions 15.11, 14.16, and 13.19. For more details about the problem and fix, and also there is some active discussion going on in the community. So for that, please refer to the link provided in this slide. Uh, uh, so next, let's see about how we can recover from the corruption in this case. So if the problem is only with the standby, then rebuild the standby. So if the problem is with master, so then consider restoring it from the backup. So if the restore doesn't work, then we can use PG reset wall tool to reset the data and successfully recover from the corruption. But in case of PG reset wall, there is a possibility of some data loss. So we need to use this as the last option. So we have seen two types of corruption so far. Based on these data, let's understand some general approaches to handling the corruption cases. We will see what are the best practices, how to detect corruption, and then corruption recovery techniques. We will begin by exploring how certain configuration settings, when misapplied, can lead to data corruption. Next, we will look at how administrative or management errors can contribute to corruption scenarios. Finally, we will examine how mistakes during backup and restore processes can also result in severe and sometimes irrecoverable corruption issues. So, in configuration settings, the first thing is don't set fsync to off. The fsync ensures data durability by forcing PostgreSQL to flush data to disk after each transaction. So, setting this to off disables this safeguard, meaning data may remain in memory and never reach the disk. A crash, which could be due to power failures or OS crash, can result in data corruption. Even if PostgreSQL appears to work fine, the underlying data files may be in inconsistent state. It is allowed to turn off only in testing or benchmarking scenarios where the performance is prioritized over the data safety. It is not recommended for real workloads or environments where the integrity matters. The next one is don't set full page writes to off. This disables writing full pages to wall during first change after a checkpoint. So if a crash occurs mid-write, PostgreSQL may not be able to recover the page correctly. So this can lead to silent data corruption, which is even more dangerous because it may go unnoticed. So don't set full page writes to off. So next is run with checksum enabled. So checksums in PostgreSQL are used to detect corruptions at the storage level. As Palak explained, they're not enabled by default. So it must be explicitly turned on during cluster initialization using initdb, and we cannot enable these checksums midway. However, PostgreSQL provides a utility called PG checksums, which allows us to verify checksums on an existing cluster, but server must be stopped before using it. So let's understand how administrative or management errors uh, can also cause corruption. So don't manually modify the data files in any way. So what happens is PostgreSQL data files are binary and highly constructed, managed internally by the database engine. So if we do any manual changes, so that can lead to data corruption, inconsistent indexes, startup failures. So we should not modify it manually. So the next thing is don't remove postmaster.pid. So the this file is created when the PostgreSQL uh, starts the server. So it contains some important information like the PID of the running PostgreSQL process, so the data directory path, port number, start time, and some other information. So this file prevents multiple instances of PostgreSQL from starting on the same data directory, which could cause data corruption. If you delete it while the server is running, PostgreSQL may fail to shut down properly, and uh, also it loses track of its own state. And the third thing is don't remove wall files manually. So let me explain this with an incident that led to a significant issue. So we had a server where the disk usage had reached 100% and the server was shut down. So to make some room for the server to start again, so we had written a script to remove old unnecessary wall files to free up the space and allowing PostgreSQL to start. The idea was once the server was up, the customer could either delete unwanted data or increase the disk size. Unfortunately, the script had a bug. It mistakenly removed some wall segments that were still required, specifically the checkpoint record and the redo pointer were located in a different wall segments. And the script deleted a segment containing the redo record. As a result, the PostgreSQL crashed on the next startup. So this is a very rare edge case and is currently not handled by PostgreSQL. I recently shared a patch in the community to address this scenario, and I have included the link here. So if anyone is interested, I would appreciate your review and feedback on this. And also, it is very important to regularly monitor PostgreSQL and OS logs for unusual errors. So it's advisable to set up some monitoring tools that can track these logs and trigger alerts when anomalies are detected. Next, let's see on the backup and restore aspects. So it is very important to take the backups regularly. So if we have the backups and if the data gets corrupted, so then we always have the option of restoring from the backup. It is also important to understand that we should able to restore from the backups available. For example, suppose if the backup is older than the retention period, so then we might not have the valid wall chain to restore from the data. It is very important to maintain the valid wall chain in such cases. Otherwise, we cannot recover from the corruption if it occurs. Next, let's understand how to detect corruption. So, one is to monitor the logs, keep an eye on the logs for unusual errors. Sometimes corruption can lead to crashes, incorrect results, or infinite loops. While analyzing these issues, we may end up identifying a corruption. So there are some messages like could not read block, could not locate a valid checkpoint, and there are some other messages also that indicates the corruption. Also, if the error code is XX001 and XX002, that also indicates the corruption. And there's a PGAM check utility provided by PostgreSQL, which is used to check the corruption. So we can check the logical consistency of the tables and indexes. Palak provided an overview of PostgreSQL data page layout, where it was indicated that the checksums are stored in the page header. So actually, these checksums are used to detect the corruption in database pages. When the data page is written to disk, PostgreSQL calculates a small integer checksum based on the page's content, and that stores in the page header. So later, when the page is read back into memory, it calculates the checksum and verifies it. So in case of corruption recovery, so let's explore how to recover a corrupted PostgreSQL database by understanding some uh, general recovery strategies like handling tgdump failures and finally using tgreset tool when necessary. So if the issue is only with the standby, rebuild the standby. So if the issue is with master, so then consider restoring from the backup or failing over to an unaffected standby. Evaluate whether you can reconstruct the data from another source. Only if these options are not feasible, so then try to attempt to recover the data from the corrupted database. Next, if you need to attempt data recovery from corrupted database, make sure to take the backup first. What if the recovery attempt makes things worse? So it is better to take the backup, and your goal should be to use pgdump to back up the database contents and then restore them to a new database, and then trying to fix on that database would be the best option. If you simply try to fix the existing corrupted database, so then there's a high risk of encountering future issues. So if pgdump fails due to an issue with a specific object, so consider dropping that object, especially if it's an index or temporary table. So as these can often recreated later without data loss. So if the pgdump is failing due to an issue with a specific index, you're unable to drop it. So in that case, consider doing the reindex, so which can potentially resolve the issue. So if the full database dump is failing, so then try to dump individual tables and schemas. So next, let's see how to use PG reset wall. PG reset wall is a PostgreSQL utility used to reset the wall of the database cluster. With this, we can recover a corrupted database. So it is recommended to use PG reset wall when the database won't start due to lost or corrupted wall files, so which cannot be recovered. So in that case, we can use PG reset wall to recover it from the corruption. And this should be considered as a last resort as it can result in some data loss. Yeah, that's all we wanted to share. Thank you.